we are. Welcome to the physics video lecture. psci 168, video lecture 32. We are talking about solar energy, and I'll review briefly what we did. And then I want to go into some solar energy power plants and send you guys out to look for good images. So this won't be that long, but it's very important that we get some good images on this stuff. So I'll describe what we're looking for. So let's start again with solar energy. And the way we discovered how much energy is flowing at us from the sun was kind of interesting. We just heated water. We just put some water in the sun and measured the temperature as it increases over time, and that was enough to determine the solar constant. So I will, do another little sketch of that solar radiation collector. So the solar radiation comes in here. There's water in this box. There's a surface area there. We imagine there's a thermometer sticking out that tells us the temperature. And of course, the temperature increases as it's out in the sun. And it just used the physics we knew. So we had Q mc delta T, and I've said, okay, I'm going to call it delta Q. And then we had, I'll just number these steps for us. And then we had, so that was in joules, okay, that was energy. And this was degrees Celsius. Then we said, okay, the power would be delta Q over delta T would be mc change in temperature over time. So we have a clock and we're measuring what's happening here in time. So this was power, and then finally the intensity would have been that power per area. Okay, so I'm going to use the letter I for the intensity. That's delta Q over delta T times 1 over area, and that's mc area over delta T. So this formula represents an experimental process, and I had shown on the graph that this would have just been the slope of our graph if we took our data, and if we did it right and carefully, we would arrive at this solar constant. So the solar constant is an intensity. So intensity is, the units would be watts per square meter. So I is equal to 1,340 watts per square meter. And of course, a watt is a joule per second, so we can use this, and that's how much solar radiation is coming in. We can use this to determine how much solar energy we'll be obtaining under various and assorted circumstances. Good, so that's where we had gotten. I had said a little more about this. Okay. So that is an intensity, and the units as right up here, watts per square meter. Okay, so how are we going to put this to use? That's just the experiment to determine what is really available from the sun. Okay, so I want to talk a little bit about a thing called a solar thermal power plant, and that's what I'm going to have you guys get some interesting images of. And there will also be the conversion, right? This is now energy per time per meter squared. So we could use this to gather energy, and that's all we were doing when we're heating water. But of course, we know that energy can be transformed. We want to be able to transform it to work and other things as well. Well, primarily to work. Okay, we want to get work out of it. Okay, so the next thing here is solar power plants. And the type we're going to start with, because it really works well with our heat engine discussion. Okay, in fact, you see, this was all just a thermal physics discussion. So how can you use solar energy to power a heat engine? And let's call this use solar energy to drive a heat engine. And of course, once you're driving a heat engine, you're then getting work out of it. And our later topic is going to be electricity, where we actually talk about electrical power and transmission. But for now, we're just talking about the energy and the work to drive a heat engine. That's our goal. And we're going to call this a solar thermal power plant. Spent a little bit of time on this. Right now I'm just going to send you guys out and look for them. Okay, so what is going on there is the following. This type of power plant has a central tower. So this is a tower, say a steel tower, and it's got this giant cylindrical container on it that contains some kind of fluid. Then there are things called heliostat. I'll put a heliostat right here, and that is a big reflecting mirror. Okay, it's standing on the ground here, and solar energy comes in from the sun, and it is reflected onto the central tower. So this here is the central tower. This mirror here is called a heliostat. And this mirror has to be motor driven because the angle of the mirror tilts throughout the day, so that as the sun goes across the sky, the reflection is always onto the central tower. Okay, so the heliostat is a driven, controlled mirror, and there's not just one, there's an entire field of them, much bigger than a football field. Okay, an enormous field of them. All the rays are concentrated on the central tower, which becomes enormously hot. Okay, so now I have to draw some piping here. So there is some fluid in here, and this will be the pipe that's leaving it, and here's a pipe that's entering it. So I've got arrows going up here into the thing, into the central tower device, and I have one leaving it. Okay, so those are my arrows here. So the one that's leaving it goes to a storage tank that holds a very hot liquid. Another tank here. Okay. So this is a storage tank at a very high temperature. Okay. And this then sends, you guessed it, very hot liquid solution here to what we're just going to call the power plant. Make it like our old powerhouse. Right? Because if you have a hot liquid, you can drive some kind of steam turbine. And power plant, let's say this thing delivers the work for us. Then here, we have a lower temperature storage, and this then goes back here. Remember, these arrows were going up into the tower, and these are going through there. So our heat engine, you could say, based on our old schematic, is this part right here. Okay. So this really fits right in with our analysis in our schematic diagram. What these are actually depends, but one solution is to use some salt that is molten salt, very, very hot, and the power plant delivers work, low temperature storage. This system can even function at night, okay? Because during the day, you're storing up all that heat, running your power plant at night. If you have enough here, or cloudy days and so forth, you have enough to continue running the system. Okay, so that's the basic scenario. There's an entire field of these mirrors, and what I want to do is list some locations that I want you guys to go look them up and get the good screen captures and everything. Okay, there's a number of these. I think the explanation here is adequate. So note about these, a whole field, a large field of heliostats. And once you see the pictures of them, you'll see it's pretty impressive. An interesting concept. A large field of these, I just drew one. There's the power plant idea. And some questions I'm going to ask here too, just lest I forget. Question: what kind of temperatures are we talking about in this system? And I've seen them before. They list them in Fahrenheit. You're probably going to want to convert them to Celsius and Kelvin to really know what's going on there. Good, so it's a solar thermal power plant. There's some other terminology there you'll run across when you look them up. Good, so I'm going to go ahead and make this list for you. And this is the homework. And of course you want to make him nice and incorporate these into your notes. That's the whole idea. So what do we have here? It's a central tower plant. Yes, okay. So homework for the images. The first one was called Solar 1, and it was near Barstow. Barstow/Daggett. Not even sure how to spell Daggett. Look it up, out by Barstow, and you'll get some good images of a power plant of this type that no longer even exists, but there are some good images online and there's some good information online. So Solar 1 is one of these. Another one is out in Kalinga. And what did I write down there? Bright source energy. So I'm going to say a bit more about what I want you to actually get from these things. But this one is out in Kalinga. It's being used for a central tower, but instead of running a heat engine here, they're actually just using the very high temperature steam that they generate out of it to extract oil from old oil fields. Okay. But it looks just like these other setups, very interesting, not that far from us. And the third one is, and you know, you guys can find more, that's fine with me. Yvonne Ha. Interesting name. That's out on the way to Las Vegas. This is the largest of those operations. So yeah, I want you to get images of these things that really make clear what we're talking about here. And in particular, I want a couple of different types of images. First of all, I want location on the map and an aerial satellite view using Google Maps. So I'm just going to write Google Maps satellite view, because you'll get satellite views that you can kind of measure the actual size of the field. Okay, so the web page will have a little scale on it that says, say, 500 feet, 200 feet, etc. So you can actually get a sense of the scale. One of these fields, and it's kind of typical, there's a field of something like this shape here. Maybe I should draw a little darker. So you're looking at the satellite view and you finally come in on something like this, and there's the tower structure will be here. This will be the north, and there's a field of hundreds, even thousands of these little heliostat devices. I can only draw a handful, but a field of these, hundreds, like I said, possibly thousands of them. And what they're doing is the top view. They're aimed at the central tower so that the rays of the sun, come in here and bounce to the central tower, which is out of the board. Okay, central tower is out of the board right here. So this is the kind of thing you'll have a view of, and if this is your web page, and right, we want to get some good screen captures of this stuff. This is your web page, and there's a little, there's a little thing that says 500 feet down here, or meters, however you're dialed in. Then you can get an idea how large this thing is. Now here's the thing. If you have so and so many meters times so and so many meters, then you have an area, and you can then estimate how much of that area is actually covered by mirrors, because of course there's spaces between them. That's an estimate. It's up to you. And then, based on our knowledge of the solar constant, you could actually estimate the power output of this power plant, and it would be kind of fun to estimate that and then look them up and see what they claim to deliver. Okay, and we make a good conservative estimate, but we should be able to be pretty close. Okay? Just like with our hydropower estimates, we can pretty much nail it with those formulas we use. Here it's a little more of a judgment because we don't know the efficiency of these mirrors. If they have dust on them, they're not as good. And we don't know exactly how much of the surface area of this giant field is actually comprised of mirror surface, and how much of it reflects onto the central tower. So what I do want for all of these is a satellite view. Interesting with Solar 1, you'll see the outline of the field, but they've removed all of the devices from it. It's still there in the vicinity. It's a bit east of Barstow, area called Daggett, and there are still contemporary solar test plants and stuff out there. So from the satellite view, you can see what's going on in some of those things. So those are these central tower power plants, and let's see what you guys get for that. Conceptually, it's right here on the board. Okay, this is what we've been studying. We know our solar constant. We get some of these areas, we can get some estimates. But for now, I'd like to see how well you can get some of this stuff. And then we'll work with what you found. It's a great application, solar power. Okay, let's see how we're doing time-wise. I'm not going to do too much more today. Yeah. In the past, I've spent a lot of time in class touring around online and discussing these things, but I think it'll be better if you guys find them for yourself and then, you know, print out some good screen captures, show me what you have when you turn in your notes. So I will add to this homework here 4. And, you know, I'm not sure what the best one is, but yeah, for a heliostat field, so say you have a nice printout of a heliostat field like this one, and, you know, you've got the scale down at the bottom. Estimate the area of the field. Field, that legible? So estimate the area of the field and the area of the mirrors. You know, it could be a half or a third or a quarter or something. See what you do. But if you actually, that assumes that you have a nice printout of one, a scale on the bottom, and you can assign an estimate to that and write it, you know, write it on the margin of your printout. So that would be for one of those. The other ones, you just want some images that show basically the details of what I'm drawing here and how that all works. Okay, good. That's a good assignment. I think you'll enjoy flying around there. It's better for you guys to do it because seeking out these places here, and like I said, satellite view map, you're going to learn some geography, some local geography, you know, zooming in and out to actually locate where these places are. So maybe a zoomed out one where you can locate them, and then locate them, then you can zoom in and show some of the apparatus. Good, we'll leave it at that. I hope you enjoy it, and see you guys next time.